Hello and welcome to the Daily Space for Thursday, July 26th of 2018. I am your host, Dr. Andres Plazas, and as always, we're going to bring you a run-up of today's news from space and astronomy. Dr. Pamela Gay is back, and she will actually be with us after the Daily Space in Learning Space with a special guest, I believe. So yes, so stay tuned after the news today. And for today, I selected two stories. So one of them has to do with gamma ray bursts, and the other one with black holes at the center of the galaxy. But let's start talking about the first story today. And in this story, astronomers using the ALMA array in the Atacama Desert studied a cataclysmic stellar explosion, as we know as gamma ray bursts or GRV, and they found what they call the enduring afterglow. So this rebound, or the way they call it is a reverse shock, actually triggered by the powerful jets from the GRV, from the gamma ray burst, slammed into the surrounding debris, and it actually lasted thousands of times longer than what they expected. So this is a massive star that is, well, this is the result from a massive star that is about 2 billion light years away from us, and collapsed and triggered a supernovae and then formed a black hole at the center of the collapse. Then this black hole actually emitted a very intense flash of the gamma rays. That's what we call it, the gamma ray burst towards the Earth, and this was detected by the space telescope, the NASA space telescope Swift Observatory on December of 2016. So actually, these gamma rays from the burst they disappear just a few seconds later. However, we still have emissions in other wavelengths. So we have X-rays, we have visible light, we have radio light, and they actually continue to shine for more than a few seconds, even up to weeks. So this allowed astronomers to study the aftermath of this event. And in addition of detecting this event with the Swift Observatory, they used different ground-based observatories, as I said, ALMA, and another one that they have used is the the Very Large Array. Um, in the case of ALMA, which stands for Atacama Large Millimeter Submillimeter Array, they actually, well, by definition, the astronomers were able to uh, do an extended study of this explosion at the millimeter wavelengths. And this actually gave them new information and new insights on the particular nature of the gamma ray burst and the size and composition of the jets. The data from the millimeter wavelengths carries information about how the jets interact with the surrounding dust and gas, and it is therefore a powerful proof of these violent and cosmic explosions. So the scientists were able to produce with the observations a time lapse movie of the event that you can maybe appreciate a little bit in the upper left corner of the screen. Uh, and yeah, so maybe you don't see it that well, but maybe I'm gonna try to play it again, which I think is rather cool. And this is the first time ever that they produce this type of time-lapse movie of this cosmic explosion. And they were surprised by how this reverse shock wave actually lasted that long. And they said that with the current understandings of GRVs, of gamma ray bursts, they would normally expect a reverse shock to last only on the time scale of a few seconds or so. This one lasted about a portion of an entire day, a sizable portion of an entire day. So the researchers explained that this type of reverse shock occurs when material is blasted away from the gamma ray burst, um, and then it runs into the surrounding gas as it's going out into the jets. It runs into the surrounding gas, and this is an encounter that slows down the escaping material. And then this encounter sends back a shock wave back to down the jet. So the jets are expected to last no more than a few seconds. So that's what they were thinking, that the reverse shock should also equally be short-lived like that. But apparently that's not the case. They actually think that the observations in the submillimeter might be the key to study this type of event and type of timescale. And because the light of this reverse shock shines most brightly at the millimeter wavelengths on the time scales of about 1 day. And they cite this as one of the particular reasons why it has been very difficult to detect previously because of the longer time scale than expected. And in addition, as I said before, in addition of this millimeter light that was created, then we also have information from X-rays and from visible light that comes from the blast of the actual shock wave carrying ahead in the jet. So the researchers explain, one of the researchers is that one of the things that one of the things that is unique with respect to this event is that this reverse shock wave entered the jet itself as the jet was moving forward away from the event, and that reverse wave was slowly but continuously transferring the energy from the jet into the forward moving wave, um, causing the X-ray and the visible light to fade much slower than expected. And then they say that astronomers have always puzzled where the extra energy in the blast of the waves comes from, because they could see the aftermath in the X-rays and in the visible even for a longer time, as I said, even up to weeks. And they had the puzzle of, well, there must be some extra energy that is causing this. And they think that um, this extra energy, thanks to the data from ALMA, comes from this reverse shock wave. They even they even quantify this, and they say that up to maybe 85% of the total in the case of 85% of the energy in the total in the case of this event is comes from this particular reverse shock wave. So they say that the uh, gamma ray event itself faded within a few seconds. Then the brighter reverse shock emission faded away within a week, and then actually this blast gave the opportunity of ALMA to study the geometry of the jet itself. So understanding actually the shape and the duration of the outflow from this event from the star is essential for determining the true energy of the burst. And in this case, the astronomers find that the jets contain as much energy as our sun puts out in a billion years. But then one of the students involved in the analysis, they say that even though this sounds like a lot of energy, which actually it is a lot of energy, but well, you have to put it relatively to what? And then the student says that it is actually one of the least energetic events that they have seen. So, and they still don't know why this is the case. But then on the other hand, they said that even though it's about 2 billion light years away, this gamma ray burst event is actually the nearest of such events for which they have measured the detailed properties of the outflow. Think this is thanks to the combining the power from the ALMA observation and the other observatories, such as the Very Large Array. Then the role of the Very Large Array is to observe at longer wavelengths, and then it continues observing in the radio wavelengths the emissions from the shock wave, from the gamma ray, from the remaining of the initial explosion. In this case, the reverse shock wave after it had faded from the detection of ALMA, which is in the submillimeters. So yes, this is I think a very cool story. In particular, the animation that they were able to do with the data that they took over the couple of years. So yes, this is one of the very interesting stories that I found today. And the other interesting story that I wanted to share with you has to do with a test of general relativity near a supermassive black hole. Um, this is a very interesting, a very cool measurement. Um, Astronomers over like 26 years, they gather data and then they look at the center of our galaxy. We know there is a massive black hole there, but then surrounding the black hole we have stars that are actually orbiting around the black hole. That's one of the reasons why we know there's a black hole there. And then there was a question of how well the theory of gravity predicts actually the dynamics of the system. And one of the things that we want to do again is to confirm this theory of gravity in different regimes. And you may find out every day and every time, well, not every day, but very sometimes often, journalists report this type of news as Einstein was right again. And but don't let it get bored. Don't let it get boring or like as a routine. I think this is fantastic that we are able to test the best theory of gravity that we have in different regimes. So a few weeks ago, I remember we were talking about the test of gravity in extragalactic scales, and that was the first time we were able to do so using gravitational lensing. So now the news that we're going to discuss today have tested gravity for the very first time this close to a black hole. And this is pretty cool and very exciting. This is amazing. So these observations were made with the European Southern Observatory Very Large Telescope. And this is, as I said, a campaign, the result of a 26-year-long observation using this one and other telescopes from the European Southern Observatory in Chile. Do we know that there is a black hole at the center of our galaxy? It's about 26,000 light years away. And it has a mass of about 4 million times the mass of the sun. And as I said, it's surrounded by a small group of galaxies that is orbiting the black hole at a very high speed. And this is at a very extreme environment. This is the strongest gravitational field in our galaxy. And as I was mentioning, it makes it one of the better places to explore the limits of gravitational physics, and in particular, to test the theory, the Einstein's general theory of relativity. So they have used infrared wavelengths, infrared observations. We need infrared because, of course, the black hole is surrounded by all this dust, and then if we want to see it, we need to use infrared that is able to see it. They have used the instrument called Gravity, another instrument called Symphony, and another one called NACO, NACO. And all these instruments on the Very Large Telescope, and they have looked at this particular star that they call S2 as it passed very close to the black hole during the month of May of this year. So at the closest point, this star was at a distance of less than about 20 billion kilometers from the black hole and moving at a speed of about 25 million kilometers per hour, which these are all huge numbers, but the point is that this type of speed is almost about 3% of the speed of light, and that's pretty fast. And actually, it actually this distance actually gives us hope to detect one of the effects, the predictions from general relativity. So this star orbits the star called S2 orbits the black hole every 16 years, more or less, in a very highly eccentric orbit. And so the team actually compared the position and the velocity of the measurements from these instruments, Gravity and Symphony, with previous observations of S2 that were made using other instruments. And one of the cool things that they did is they calculated the predictions from Newtonian mechanics. This is from the laws of Kepler, the laws of Newton, and the predictions of general relativity. And they measured something that is called the gravitational redshift. So this is in particular, what does this mean? This is means that the light from the star is stretched to longer wavelengths by the very strong gravitational field of the black hole, and this is a consequence of the time dilation that we are experiencing close to the distorted, well, close, as I said before, but still relatively close, but close to the distorted space-time caused by the intense gravity field of the black hole. So you may know about this, but for example, the classic example that I now cite is the movie Interstellar, when one of the astronauts goes to a planet close to a black hole, and then um, he says that 1 hour in that planet is about 7 hours in on Earth. I'm sorry, 7 years on Earth. And then it's funny because well, it put this into pop culture, and then you saw a lot of memes saying like, oh, I should go there and do my PhD, and haha. But yeah, the point is that as a consequence of this time dilation, then the photons coming from a place that is close to an intense gravitational field are actually going to lose energy, and we're going to observe a redshift. Actually, the light from the photons are going to move towards the redder wavelengths. And then this particular change in wavelength of light from this star agrees precisely with what is predicted by by Einstein's theory of relativity. And this is the first time that this deviation from the predictions of the simpler Newtonian theory of gravity has been observed in the motion of a star around a supermassive black hole. So one of the very interesting plots that they had in the paper, so I looked at the paper on the archive, is this plot that you can see on the screen right now. And yes, on the horizontal axis you have time, the observation throughout the time, and on the y-axis you have a measurement of a difference between the redshift predicted by the general relativity and the redshift predicted by the Keplerian theory, which in other words is the Newtonian theory. And the red solid line that you can see there is the prediction from general relativity, and then the horizontal gray line at 0 is the prediction from Newtonian dynamics. And then you can see how the newer observations, all the circles in green, they follow the prediction from general relativity within the error bars. You can see how the observations before the year 2017, more or less, the ones that are in white circles, they actually more or less were consistent within the error bars with Newtonian dynamics. But then the new observations, you couldn't tell, right, because of the error bars. But then the new observations actually have showed us to actually a high significance, and in the paper they cite a significance of what they call 10 sigma, which means like a lot. There is a very tiny probability, very tiny probability that this is due only to chance. And they observe how the data points are consistent with the hypothesis of something different from Newtonian dynamics. And then I say this in a little bit convoluted way because in the press release, of course, they say that, and I have been saying, that it's consistent with GR, and that Einstein was right, which is true. But one of the little details that you can see in the paper is that actually it could be consistent with the deviation from general relativity. So they use a number to quantify, a number between 0 and 1 to quantify if you actually follow Newtonian dynamics or if you follow precisely GR. So 1 is GR, general relativity, 0 is Newtonian dynamics. And they get a number of about 0.97 plus or minus something that puts them into the 1, right, within the error bars. But my point is that there's also room to maybe find out that something that is different from Newtonian dynamics, but at the same time is also different from GR. So they don't have the error bars yet to determine that. They do tell that you can rule out the description by Newton. And you would need more observations, of course, and more detailed observations to actually try to identify deviations from general relativity, which is, as I said a lot of times here in the daily space, this is one of the things we want to do. We want to see if actually we need a more precise description of gravity than that that Einstein's theory gives us, which so far hasn't been the case, right? So yeah, that's what I wanted to say for today. And let me see if you guys have any questions, any comments before we go to the learning space by Dr. Pamela. So now I'm gonna go back to the chat and say hi to everyone, to Paranor 001. I'm gonna say hi to the Nightbot, even though the Nightbot cannot hear me. I'm gonna say hi to Nancy Grass. Hello. DPI 201. Hello. Denizen of Earth. Tom Fans Cutter. Guido B. Larry. Weird and Proud. Hi. Dr. Pamela is back. Yeah, we're all happy. She wasn't here today for the daily space, but she will be here later for learning space, and she will be here tomorrow for the daily space as well. It's a lot of space in CosmoQuest. Guido B, good evening from Germany, 34 Celsius. That's warm, so enjoy. Larry says that it's also warm in Austin. And hello, Hannes Warverb. Sorry about the stream title, says Guido B. Don't worry about it. Thank you for your help. What is the elemental composition of the jets? I think it's just gas, the material that is accreting around the black hole. So yes, I think it's just a stellar gas, probably some object that was, I don't know if it was actually shredded by the black hole, or maybe remnants from the actual explosion from the original star that caused the supernovae, that ended up in a supernovae, and then that ended up forming the black hole. Does the gamma rays in these gamma ray bursts transmute into particle pairs, particles and antiparticles? If so, what particles are they? Yeah, that's a good question, and I'm actually not sure. I know there must be very energetic particles, but I'm not that sure if actually there is some sort of annihilation. And yeah, we'll have to check that. Here I might be speculating that it might be actually, it could be some sort of particle-antiparticle annihilation that produces the gamma rays. But I'm not so sure in this particular case about that. Does the shock wave travel at the speed of sound in the jet? I would say yes, but that's another thing that I have to check. So, well, by definition, without me checking now, by definition, if it's a shock wave, then it's gonna be faster than the speed of sound in that particular medium, and that's gonna depend on the composition of the medium and then how the actual the wave vectors travel in the medium. Any place that S2 has a planet or two? I don't know. That's a good question about that star. I'm not sure. I don't know. It's a very elliptical orbit. I don't know if people have been able to do observations by that. I know a lot of people from the UCLA have been doing a lot of observations of this, but I don't know if they have reported like a planet going around this particular star. Oh, I think I skipped another question. Sorry for that. Hannes Verb. What effects does this have on the star? Are the lives shortened by all the stress? Well, in the frame of reference, life is just life, and but if you actually compare that particular point in that gravitational field, you compare it from a different point where the gravitational potential is not, where the gravitational strength is not as strong, then you can tell the effect of the time dilation from the point of view of the other reference frame. But in the reference frame, there in the star, then they just their clocks are just ticking at their particular whatever rate is ticking. So you need to compare it with another reference frame, and with respect to the other reference frame of, for example, for us, or like in the movie Interstellar, with respect to the reference frame of the Earth, then the time in the planet is different, so it goes slower, and vice versa. Then Einstein, that's true. Yes. Hello, Ambius. We have a Star Strider and says they're ready whenever, so that's good. I think we're gonna be ready soon. Um, oh yeah, but did he publish any of those things he was wrong on? Um, are you talking about Einstein? Um, this is a question from Ambius. Did he publish any of those things he was wrong on? I don't know. I'm speculating. I don't know. It makes me think, for example, that Einstein predicted, he calculated like in 1912 before he got general relativity done in 1915. In 1912, he was already thinking about the effect of gravitational lensing due to this, and then he concluded that, he thought he was, thinking about a star, and then he concluded that the effect would be too small to be detected, and then he never published that until like 1936 or something like that, when some other guy from the Zurich Institute told him you should publish this. And then Einstein even wrote a paper in Science saying, okay, I wanna be nice to this person and I'm gonna publish this calculation, but I don't think this is right. And and yeah, this is the calculation. And it turns out that, like 100 years later, we were able. Well, people actually then, realize that if you have a larger body that acts as a lens, like a galaxy or cluster of galaxies, then you're going to be able to measure the effect of gravitational lensing. With a star, indeed, the effect is very tiny. But then in the last year or so, we were able to actually detect the gravitational lensing by a single star other than our sun. That's one of the things that he was wrong and he didn't publish. And one of the things I'm interpreting your answer. Have they ever proven Einstein wrong on anything? Uh, maybe not wrong, but at the end of his life, he was working on a theory to unify, like a theory of unification, and that was never successful. One of the famous blunders, and he called it the biggest blunder of my life, is the cosmological constant, because back in the time he believed in a static universe, and his equations were giving him a expanding universe, but he didn't trust his own equations. And then some other guy came from Russia, actually Alexander Freeman, and told him actually the equations tell you that we have an expanding universe. So Einstein wanted to make a static universe, and he put a mathematical term by hand to make it a standard to prevent it from expanding. And then, long story short, a decade later, Vestus Leifert and other people like Hubble actually empirically showed that the universe indeed was expanding. And then he famously called himself that mathematical term that he introduced into his equation as his greatest blunder. And then the story that they tell is that many decades later, people actually discovered that the universe is expanding, but faster than we thought, faster with time, and we don't know why that's happening. So they say, what if we put a mathematical term with the right sign that can get us what we observe? And then they were able to revive that cosmological constant from Einstein, but with the opposite sign, not to make the universe static, but to make it actually expand at a faster and faster pace with time. Einstein also worked in molecular theory and in quantum mechanics, and he was very fundamental to the beginnings of quantum mechanics. But as far as I know, those were like good calculations. He actually worked on Brownian motion and the motion of the atoms. He worked on the photoelectric effect. That's why he got the Nobel Prize. And all these calculations were actually right. Then people came out with something more precise and robust. But yeah. Envy is pretty warm in Israel as well. Yeah. There's a heat wave in the earth. What what if S2 gets closer to Saga A star? That's the black hole at the center of the universe. It is time diluted in reference to us. It is. If so, how much? Um, I don't know the exact answer to that. There is a formula in general relativity that tells you that the delta t or the time dilation, and then you can actually calculate that if you know the mass of the objects. Then you can calculate that using general relativity, using one of the metrics, the Schwarzschild metric, for example. Well, anyhow, and this is one of the things that Kip Thorne did for the movie Interstellar. He wanted, the director came, Christopher Nolan came to him and told him, I want a planet where 1 hour here is 7 years on Earth. Given those constraints, you can go back to the formula and then calculate how much mass you need and then how close to the star, to the black hole you would need to be, and then you would get your answer. So given that would be like the problem backwards, but now if we know that we're much this closer to the black hole or to the event horizon, and then we know the mass of the objects, there is a formula that's going to tell us what the delta t is, which I don't remember. Not annihilation, creation, the reverse process. You're right, Larry. I was thinking maybe annihilation of photons that produce gamma rays, which is something, for example, that the Fermi satellite gets. So maybe that's what I was thinking. Mhm. The a cappella science guy, I don't know what it is. He sometimes didn't believe what his theory was saying, like black holes, I think. Yeah, I think that you have all these prejudices from scientists or the prejudices from the time, and even Einstein himself, in the case of the expansion of the universe, he could have predicted the expansion of the universe, but he decided to go with the flow of the time. And well, that's fine. We're humans, but of course we should learn from all these lessons from history. And it doesn't matter if today then any authority in science comes and tells us something, or somebody else, or I don't know. This is what the most of the people think. In the end, you have to do experiments. And don't get me wrong, scientific consensus is important. So having scientific consensus in a community, it tells us and us. It just we're not gonna go all the way and just don't believe anything. And it is very important to have an independent team of experts from everywhere to actually agree on something and then say, to the best of our knowledge, we think that this is it. But in the end, if we come up with new experiments and new experiments and new experiments that is telling us something different, then we need to pay attention to experiments. That's the way science works. He also famously hated a lot of quantum mechanics, but I don't think he ever published any of that. I don't know if he formally, I don't know if the word is hated, but he was just skeptical. And he did, in his papers, he did say it, he like, this doesn't sound right, and this is why I think, and he did some calculations as well. And in the letters, we know that the letters that he wrote to other scientists like Bohr or I don't know if Planck, maybe with Planck, but we do know that he was vocal in his skepticism towards the new theory of the quanta, more exactly by the probabilistic nature, that makes them feel a little bit uncomfortable. Um, okay, I think maybe it's time to give some space to the learning space and to Dr. Pamela, who has a guest today. So thank you so much for watching, everyone. This has been the Daily Space, a production of CosmoQuest, created by the Astronomical Society of the Pacific. And our goal is to put science in your brain. So if you like this show, please give us a follow, or even better, please consider subscribing. And please stay tuned to see Dr. Pamela Gay in the learning space. And our daily space will be back tomorrow every day, every weekday at 1 p.m. Eastern, 10 a.m. Pacific, and 6 p.m. London. And we will have Dr. Gay back. So, yeah. Thank you so much, guys, for being with me this week. And I'll hope to see you again in the future. Adios.